We are going to start on page 24 today. We're going to talk about something called the number E. So E is a number we'll see that's similar to pi would be our probably best comparison. So remember, pi is this non-repeating, non-terminating decimal, and we get it from looking at the ratios involved in measurements in a circle. Okay, so pi represents something, that something isn't an exact value. We use the constant, the Greek letter pi, to be able to represent it. So as we look at E today, I'm going to start by talking about where E comes from. So if you put money into a bank account, like a savings account, you earn interest on that money. So if you have a savings account, about every 3 months or so, you see there's one extra penny in there, and that's a payment from interest from the bank. So the bank has set amounts of times that it compounds interest each year. Most commonly, I think it's quarterly for just a regular old savings account, but it could be just once a year, twice a year, it could be monthly. The amount of money that you have at the end of the year can be represented in some exponential functions that we're going to take a look at here in just a second. So we're going to take a look at what these functions look like without any values plugged in, just in sort of a generic form. And we're also going to take a look at what they would look like for a specific example. Let's say I have $100 in my account at an interest rate of 14%. In real life, that would be like 0.02% or something like that, not 14. But we'll take a look at 14% compounded for 5 years. And so we'll look at what happens when I compound this money, when I calculate that interest, calculate and collect that interest at different intervals throughout the course of the year. So my generic form is to say n times a year. I haven't decided how many times a year yet, or I don't know how many times a year yet. Yearly means my n value is 1. So we can see for an n of 1, we've plugged in. For yearly, we've plugged in 1 here for n. Now for my specific example with that $100, at 14%, right? $100, 14% for 5 years. I plugged in values for all of these other pieces of my function. And this is how much money I have in my account at the end of that year, including the interest that I've collected. Quarterly means 4 times in a year. So that means my n value would be 4. And that would look like this with 4 plugged in for n. Now for our $100 example, I've got my $100 at 14%. Over the course of 5 years, compounding quarterly, we would get a little bit more money. So once a year, I get about $192. 4 times a year, I get almost $199. Monthly means 12 times in a year, I'm going to compound my interest. So we see our 12s here. And in our specific example with our $100, and now I'm at just over $200. Okay, so a big jump between yearly and quarterly. Another jump between quarterly and monthly. I'm compounding more times, so I earn a little more interest. What about daily then? So if I compound interest every day for a year, that would be 365 for my n value, and I would get a little over $201 compounding daily. Okay, so the more times I compound, I get a little bit less difference in between these values. But if I look at daily compared to yearly, that's not a bad amount of money, an extra about $9 for not doing anything. That's not too bad. Let me scoot that up there. So then the question becomes, well, if I earn more and more and more money by compounding more frequently, how often can I possibly collect this interest? How often can I possibly compound my interest? And so the goal is that I am always calculating and compounding interest. So daily would be every day, but can I compound more frequently? Can I compound every hour or every minute? And so what we get to is something called continuously compounded interest. And we modify our formula a little bit for continuously compounded interest. And here's where we have E start to pop in. So C is still that initial amount of money that we started with. R is still my rate, and T is our time in years, just as T was our time in years above as well. And so for our $100 example, there's our $100 at 14% for 5 years. And we get even just a little bit, not a ton with our $100, but even just a little bit more money compounding continuously. So compounding continuously gives us more money. That's the ideal amount of times I would want to compound. That's how I can make the maximum amount of profit in interest in my bank account. And what happens is I'm letting this n value, when I compound continuously, I'm letting this n value get close to infinity, closer and closer and closer to infinity. As I let this n value get closer and closer and closer to infinity, we'll take the t part of it away for just a second. As I let that value get closer and closer and closer to infinity, this number as a whole gets closer and closer and closer to this value, 2.718, blah, 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 blah. And I should have some ellipses behind that because this number doesn't stop at the 9, it keeps going. Just like pi keeps going, e keeps going as well. So when we see e, that's a constant, just like pi is, and it's this 2.718 blah, blah, blah number, okay? So when we see e in our formula here, that's not a variable, that's a number, again, just like pi. And if we compound continuously, what we say is that instead of having to plug in infinity here, which gets a little hairy, we just use that constant, okay? We use that constant here instead. So let's take a look at e. That's what we're going to spend the bulk of our time on today. Let's take a little bit closer look at e. So e acts just like any other number. If I'm looking at e with some exponent, which we frequently will be in our exponentials unit, then I combine my terms with e the same way I would combine my terms with any other value. So for number 1, I've got 2e times e to the negative 4th. So if I'm going to combine my terms here, I want to combine my like terms just like I would if I had x's or 7s to some power. I would add their exponents. So here this would be e to the 1st. 1 plus negative 4, that would give me 2e to the negative 3rd. And I could write this as 2 over e cubed. So I had a positive exponent there. Same exponent rules that we've learned over and over again. For number 4, same idea. I'm multiplying things that have the same base, so I add their exponents. Negative 2 plus 5 would be 3, so I have e cubed here. For number 7, I've got a power to a power. So the outside power distributes in. This would be 2 cubed times e cubed to the 3rd, power to a power, we multiply. 2 cubed is 8, so I'm going to go ahead and simplify that since I know what it is. And then e to the 9th, 8e to the 9th there. For number 2, I've got some division happening here, so I'm going to follow my exponent rules again. Now 6 divided by 2 I can simplify, that would just be 3. And then for my e's, and the exponents are even a little messier here, e to the 5x and e to the 3x, I still follow the same exponent rules. So I take the bigger number, subtract the smaller number, so 5x minus 3x is 2x, and it will stick where that bigger exponent was. It will stick on top. So 3e to the 2x. For number 5, I'm going to start by multiplying those coefficients there. 5 times 4 is 20. And then for my e's, since I'm multiplying things that have the same base, we add their exponents. So that would be e to the 5th, 20e to the 5th. Number 8, similar to number 2, I've got e to the 5th divided by e squared, subtract their exponents. Big minus little would give me e cubed. 5 minus 2 is 3. And then this would stick on top. So I could write this as over 1 or just e cubed here. For number 3, again, I've got an exponent outside of parentheses. So I want to distribute that in. Now we need to be careful because this is negative 5. I take a negative number to a power. I need to be careful with that. And then on that e, I already have an exponent, so I'll multiply it by the 3. Negative 5 cubed would be negative 125. And then e to the 6th. For number 6, similar idea to what we saw in number 2, again with those a little bit more complicated exponents, but this is what we see with our exponentials, right? We've got x in the exponent, so this would be e to the 6x. Same base, add the exponents. And then finally for number 9, 10 divided by 2, that would be 5. And now big minus little to combine my e's, this time my bigger exponent is on the bottom. So 4 minus 2 would be 2, so I have e to the 2nd power, e squared on the bottom. All the same exponent rules we've seen before. The next thing I want to take a look at is actually evaluating things with e. Now remember, e is a number. So this e squared I could simplify. Same with e cubed or e to the 9th or e to the 5th, e to the 6th. I could simplify all of those. So I'm going to show you on your calculator how we do that. We actually have a key for e. So I'm going to pull up my calculator here. And let's go ahead and add a calculator page. We do this on Scratchpad as well. And your E key is off to the side. It's right next to 10 to the x, which is just to the left of 1. So e to the x. So for number 10, it wants me to evaluate e to the 2/3. So I'm going to hit this key. And the default for your TI Inspire is to give you a box to type in exponent. If you just have e, you could type in a 1 there for e to the 1st. We want e to the 2/3. So I'm going to type 2/3. And I get 1.947. It said round to 3 decimal places, so 1.948. For e to the 4th, same idea. I'm going to hit that e key and then to the 4th power and hit enter. If I round to 3 decimal places, I would get 54.598. And then finally 2e to the negative 1/5. So I want to multiply by 2 first. So 2e, don't forget to use your negative, to the negative 1/5. Okay. And I get 1.637 if I round to 3 decimal places. So E key right over here on our calculator if we need to evaluate things with E. Okay. I do want to point out a little difference in directions here so we know when to do what. For the top of page 25, our directions say simplify. So we keep E to whatever power. Towards the middle, it said using E on your calculator, it told me to round to 3 decimal places. If it were to say something like evaluate, then I would want to actually type that in my calculator. So just something to keep in mind. The next thing I want to look at is going back to those interest problems. Okay, so we're going to deposit $1,200 in an account that pays 5% annual interest. After 10 years, you withdraw the money. Find the balance in your account if the interest was compounded all of these different times. So this is back to those functions that we have listed on the last page. This is what I'm going to pull from. And so remember, yearly means my end value is 1, quarterly it's 4, monthly n is 12, daily 365. And if I see continuously, I have to use that modified continuous interest formula. So on page 13 or on page 25, number 13, we're going to set up what this looks like and then type it into our calculator at the end. So for yearly, this would be my $1,200 times, in parentheses, 1 plus 0.05 over 1. We're compounding once in this year. And then my exponent would be 1 times 10. For quarterly, this would be 1,200 times 1 plus 0.05, my interest rate, over 4. Quarterly is 4 times in a year. And then my exponent is 4 times 10. Monthly, everything stays the same except for that n value. So for monthly, our n is 12. Our interest rate is the same. Our initial amount is the same. Our time frame of 10 years is the same. For daily, again, everything's the same except that n value. So my rate will be divided by 365. And then in my exponent, 365 times 10. Continuously is where things change a little bit. I would have my $1,200 times E, and then my exponent on E would be the rate times time, times my years. So we're going to go to our calculator and type these in. Let me pull my calculator up here. Again, just on the calculator page is fine. So I'm going to start with my $1,200 and times in parentheses 1 plus. If you want to write your 0.05 over 1, you can, but that would just be 0.05. And then this is to the 1 times 10 or the 10th power. So we would get, remember, since this is money, I want to round to 2 decimal places. So we would get $1,954.67. I'm going to do this again now, compounding quarterly. So $1,200 times 1 plus. Now this time I do need to set up that fraction, and for the rest of these I will. So I'm going to hit Control Divide so I get that fraction there. So 0.05. And then on the bottom here, quarterly is 4. And then arrowing out, I want my exponent outside of those parentheses. This would be 4 times 10. And this time, compounding quarterly, I've got $1,972.34. I'm going to cheat a little bit and just modify instead of typing in from scratch again. So we're now compounding monthly. So this end value switches from 4 for quarterly to 12 for monthly. Everything else is the same. Now I'm making $1,976.41. For daily, I'm going to cheat again and copy this and edit it. So for daily, 365 is my end value. Oops, arrow back over here. And 365. So when I compound daily, $1,978.40. I know the 0 isn't there, but we would write it when we talk about money. And then finally, for compounding continuously, this time I'm not going to copy because it's a different formula. So 1,200 and then E to the 0.05 times 10. So we get $1,978.47 this time. Okay. So I recorded all of those values as I got them from my calculator. I got them here. And then what I see as I increase the number of times I compound my interest in a year, I earn more money. Okay. The amount in the account. And remember, that's what this number is. It's that total amount in my account, including my original principal of $1,200, as well as the interest I've earned over the course of the year. The amount in the account increases as the number of compoundings increases. Okay. The more often I compound interest, the more money I make. The very last thing I want to take a look at today is a graph of E. So we'll look at the parent function and then a transformation there. This is just an exponential function. Remember that E is that 2.718 number. So this would be about that. So E is more precise than this, but this is about what we're graphing here. That's what we're saying when we want to graph E to the X. So my asymptote would be at 0. I'm going to go ahead and sketch that in on my graph. My asymptote's at 0. My key point would be 1. I'm not shifting up or down. I'm not moving left or right. So just at 1. So if I'm keeping a little table here to keep track of some X and Y values, I've got a point at 0, 1. If I want to find points moving forward, this is my growth rate. So I could take this distance and multiply it by 2.718, or you could just plug some more values for x in. So I'm going to plug in -1 and +1. We'll go up to 2. So if I plug in +1 to my exponent here, I would just get about 2.7. It'd be really difficult for me to graph anything more precise than that, so I'm just going to leave it at 2.7. So 2.7 would be right about there. If I plug in 2, I'm going to square this 2.718 and multiply by 1. That gives me 7.4, about, technically 7.389, but we'll do 7.4. So 1, 2, 3, 4, 5, 6, 7.4 is about there. If I went backwards the other way, I would have e to the negative first power. And that would be about 3.68. So we'll say about 0.4. So back this way, we're at about 0.4. Remember, when you graph an exponential function, 3 points minimum and your asymptote, sketching your curve once you've got all your points. Okay, so I treat this just like any other exponential function. If I had maybe a more complex function, I could do the same thing. I would start by finding my key point. So again, I would expect a 1 in front here since I don't see anything. And my asymptote, I'll graph my asymptote first. So our asymptote is at 3, 1, 2, 3. Okay. And then our key point would be 1 unit above. So it would be at 0, 1. And then add 3 to account for that shift up, subtract 1 to account for the shift to the left, and we get our key point to be -1, 4. So I could put that in my table. So -1, 4. I want you to notice that this is a transformation of our parent function key point, including those shifts. So up 3 units and right 1. So I could actually find all the other points on my graph by shifting these to the left one. I believe I said right one a second ago. To the right, to the left one, sorry, and up 3. So if I shifted this back to the left one, that would be the point 0. My x coordinate, I should say, would be 0. And then up 3, that would be about 5.7. So 0, there's 4, 5.7. I could also, if I wanted to, just pick some more values and plug them in for x. Okay, so however you choose to do this, transforming our values here in our tables, I'll do this one with the transformation again. This isn't too bad. So to the left one means instead of 2, I'd be at 1. And then up 3, right? That's what this is telling me. Up 3, that would be 10.4. So 1, there's 3, 4, 5, 6, 7, 8, 9, 10.4 would be right about there. Or you could plug in your exponent. So this would be e to the -2 plus 1 plus 3. That would be e to the -1st. E to the -1st we know is 0.4 plus 3 would give me about 3.4. Again, this is a rounded value, but -2, you get about 3.4. So same exponential shape, still growth because e is a number greater than 1, but shifted up and to the left. Okay, so those are exponential functions with a base of e. So e is a number, again, like pi, non-repeating, non-terminating decimal. It follows all of our exponent rules. We can graph it the same way we would graph any other base for an exponent. It just has a very specific application with interest problems. Okay, so that is the number e.